Everybody, I'm going to present today a phenomenon of electrostatic in aerosol, and if we're going to have time, I'm also going to tell you a little bit about my research, which involved the position of electrostatics effect in the lungs. So when we talk about particle transport, we use the Lagrangian framework, and we actually talked about drag force, the effect of Brownian motion, the effect of gravity, but we didn't talk much about electrostatic, and that's the reason I'm here today. So when we zoom into electrostatic, before that I want to give you some motivation where actually electrostatic is play a major role. If we're going to compare two kinds of forces that actually proportional to area, like electrostatics effects, and forces that proportional to the volume, like gravity, we're going to have this ratio, and this ratio actually going to end to be anti-proportional to the radius, which means that for big objects, like Apple for example, gravity would be the dominant force, but for small objects like aerosols, electrostatic can play a major role because the area is huge. And I have a really cool example of this kid. This kid is just sliding, and the kid is huge and heavy, and that's the reason the sliding gravity dominates the motion of the kid. But look at his hair. When we think about hair, the area is huge compared to the volume, and here you can see that he has electrostatic repulsion between his hairs. Okay, so that's exactly the concept. So kid gravity, hair said electrostatics. Okay, cool. So electrostatics force is actually really similar to gravity in the concept. We have some field, gravity field, electric field, and we have the property that actually is sensitive to the field, mass and charge. And when we want to talk about the effect of electrostatic, the location, the velocity, so like we know with gravity that we have some velocity that we're going to reach, this would not accelerate to infinity if we're going to throw an object, because drag would resist it until they're going to have some balance. So we have the same thing with electrostatics. So if you compare drag to electrostatic force, we're going to get this equation. We're already familiar with this part. This is the mobility of the particle, right? And for different size of particles, we can actually understand the mechanical mobility. But if we're going to multiply it by the charge of the particle, we're going to have an extensive idea which called electrical mobility, which denote with Z. And this is just an example of particle classifier. So here you stop here at the first part, the device actually stopping the big particle to clog the system. The particle getting inside a chamber that make a known charge density on the particle, and then using electric field, we can control the velocity due to the electrical force to control the particle, and only one kind of the size not one kind, but a band of sizes gonna reach the other side of the device. So this is just an example. Another concept how to extract information about the electrostatic force compared to drag. We can use the drag coefficient, we can use the idea of Reynolds, and without knowing exactly the velocity, we can actually discover many properties using the graph that we saw in the class regarding the drag force. This is another approach, but let's zoom out and talk, okay, so where does charge comes from, okay? So most of the time we're gonna denote charge as some multiplication of the unit of charge, the basic unit, the electrons. So this is a natural number, and this is the amount of charge. So let's talk about many charge mechanisms that we have. So I'm gonna talk on three mechanical way to actually charge particles. The first one is spraying. Okay, some liquids have a charged surface. Okay, you can make a charged surface of a layer, and then you rip off this layer and take it to yourself. This is a cool example. This is called Electrospray. And what Electrospray actually do, you accumulate positive charge on the tip, and then you drag the droplets, a positive droplets. The mechanism is that you have some fluid, and you put a voltage drop, a difference of a potential, and then you pull this part by electric field, because the positive charges want to go in the direction of electric field, and using drag you actually gonna take the droplets and to wherever you want. Yes. Another mechanism is electrolyte. So if you're talking about water or other materials that have a huge dielectric constant, when they're gonna get out of a small nozzle, they're gonna be involved a lot of interaction with the solid, with the plastic itself, with the other material, and it's gonna take charge, strict charge of the surface. And another concept is not liquids, but with the actually a solid like powder or stuff like that, and which with a lot of friction, like this kid actually get from friction with the slide, actually get charged. So the same concept happens with many inhalers that use powder when the particles are not conducting. Okay, cool. In my experiment, I actually using a aerosol generator and diffusion dryers.
Quick question.
Yes.
Could you go to slide back?
Yes.
One more?
Yeah.
No, go back. So what's the difference between contact and this one?
This one?
Yeah.
This one actually involve of a liquid with a higher dielectric constant.
Okay.
And this actually this part is actually talking about material that have a huge resistance. So when particles, when charge stick to it, it's gonna stay on this material. That's the concept here.
Same with the dielectric, like?
What?
That's the same with the dielectric?
No, dielectric and resistivity are different constants of material. And this is more involved of like powders, and so here it's called dry powder inhaler. Okay. And this gain huge amount of charge compared to this one. This one is actually small amount of charge.
But the charge is gained due to friction in both cases?
Yes, in both cases. Okay. Yeah, interaction with the material, the other material. Yes. Okay. So in my case, I use polystyrene particle, and this, according to some reference that I have, gonna give me 100 electron per 1 micrometer aerosol. So what's the problem with all these mechanisms? These mechanisms are not reliable. Okay, so if you want to have a more strict way and to understand what is exactly the charge that we have, we need to use other approaches. So, and this approach is actually talking about collision between ions that you have in the medium with your particles. So the collision actually transfer the charge. So the first one is diffusion charging, which based on a random collision. And you can see here we have the ion concentration in the medium, in the air, for example, and here you will have the thermal speed of the ions, and this mechanism is more dominant for small particle. We're going to see the other mechanism why so. And this is of course an approximation. It's really complicated to actually calculate that. And one of the limitations of this mechanism is when a particle gain a lot of charge, for example, positive charge, it would not, the chances to collide with another positive ion get low and low and low, get reduced. The other one is more kind of a guided collision. I use an external electric field. The ion is not randomly jumping, and I'm gonna guide the ions through the particles. So here you have like kind of a time scale, right? And this is some particle, and this is the electric field line, which means where is actually the ion gonna go? What is the direction? So you see that the ions follow the electric field line. So in the first case, they're gonna accumulate on the charge, but as the particle gonna gain more and more charge, it's gonna repel the electric lines, the electric field lines, and again less until he would not reach at all. And so this is the equation that talk about this mechanism, and I think it's really interesting because these three parts of the equation. So the first...
The field charging is corona charging?
What, here? No.
It's not corona?
No, it's not corona. The next one is corona. Yeah, okay. So the first part, this one in the middle, is actually talking about the strength of the external electric field, which is this. If you're gonna put a huge external field, you're gonna gain more fast. It's a time dependent, more fast charging. And another thing you see here, it's depending on the area of the aerosol itself. dp square, and this is, as I said before, more dominant for a huge part, for a bigger particle because of this term. The left one is also really interesting. You see epsilon r, the dielectric constant, and this is actually relevant to the particle material, what is property, what it's made from. And you can see that these things can go to a certain range. 1 when this is equal, 1 in the small case, and when it go to infinity, you're gonna have 3. And from different material, you have different properties. Vacuum is 1 by definition, air is close to 1, and pure water is big, 80, and conducting gonna have infinity amount of dielectric constant. And the last term is actually relevant to the time. What is the speed that the aerosol actually gonna gain charge? So the constant here that I put is actually holding the properties of the ions themselves, the mobility of the ion, and also the concentration. And I want you to notice how huge is this concentration. It's 10 to the 13. So this mechanism that I talked until now only can work if you have a lot of ion and a lot of chances to collide with the ion, right? So we're gonna talk about that a little bit. So this number is huge. It's really crowded in ions. So how you actually gain this number, especially when we're talking about normal situation, when you have cubic meter, right? It's contain only 10,000 ions, but we want to have 10 order of magnitudes more. So the solution to that is actually lighting, or what's called corona discharge. So what we actually do, if we're gonna apply, we know that air is actually a resistor, right? It's like you have a huge resistivity, we cannot conduct electricity through air, but it is true until you're gonna apply a really high electric field, which air gonna break down. We're gonna excite electrons in air, okay? And we're gonna see light. We know this phenomena as thunders. So the concept is, when we have these thunders, this effect, this corona discharge, we're gonna affect the air and produce ion in the air. So for example, here you can see a capacitor, kind of, right? You have a outside tube and an inner tube. You put a difference in potential between them, and using Gauss's law, you can actually understand what is the electric field between them. You see that the electric field is increasing as you reach to the center, to the inner tube, right? And so in this inner tube, you can have a huge electric field, and this electric field can actually break down air and make the phenomena of corona discharge. And you see here, you can calculate actually what is the distance that it's gonna happen, and this is the mechanism to produce a lot of ions. And I want to say that you cannot charge aerosols as much as you want, okay? There's some limitation to it. And so in this graph, you can see many of the kind of limitation that you have. So first of all, there's a repulsion between charges. Positive and positive charges would repel each other, or negative and negative repel each other. So they're gonna be an inside electric field inside the aerosol itself, okay, of repulsion. So when you're gonna reach this amount of electric field inside a constant, inside the, this is the surface area. Of course, if they have a lot of surface area, there's a pretty big distance between them. They're not gonna sense each other, but if they're gonna dance on a small particle, they're gonna sense each other effect. So this is the limitation, the electric field inside. And we see here it's a really small, but for electron emission, spontaneous electron emission, we're talking about electric field of 9 multiplied by 10 to the 8. But for positive emission, which means ions, it's really hard. It's gonna be to the 10 to the 10, okay? Multiplied by 10 to the power of 10. So
why is the difference?
The difference, because when you think about electron emission, it's really easy. Electron not weight so much compared to the ion, which is more massive. So for that reason, the emission here is gonna be harder. So you can see here for electron and positive ion emission. Because when we're talking about positive, it's actually the thing that I don't have electron. This is the concept of being positive, right? And if you compare them, you can see a huge difference between the two methods for a single size. And another limit, it's called the Rayleigh limit, is actually talking about that a lot of aerosols are made of some liquid, mostly water, right? In most cases. So water has some surface tension. The electric repulsion can actually try to break the water droplet into smaller water droplets. So you have this kind of limitation, and you have the surface tension over here. And I want to emphasize something. Most of the time we think that there's charge, there's no charge, and actually to have no charge is a rare bird, okay? It's most of the time we're gonna have some distribution of charges. When we're gonna look at a big volume, it's gonna be natural, okay? Because positive gonna cancel the negative, but there's gonna be some distribution of charges. And that's actually called the Boltzmann Equilibrium, and or sometimes called it steady state charging distributed. So when we look about 1 centimeter cube, right? So we're gonna have some charge in the air. As I told you before, it's kind of 10 to the third ions, but positive cancel the negative, so this thing is neutral. And so this is the equation to actually understand how much fractions of charge do you have in your volume when we're talking about steady state situation. And this can be, this is G. G is a function of the charge, of the temperature, and other things. And you can have a more simplified version of it if we're talking about big particles, which is this. And I'm going to show you this graphically. So this is a calculation that I did for my experiment. So you can see for 200 nanometers, okay, you have this kind of distribution, the purple one. 30% actually gonna be zero charge, really neutral particles, but 50% gonna be positive or negative, right? And because it's a steady state, they're gonna be the same value, the same positive, the same amount of negative. And when you go, and when you go on to plus 2 and plus 2 electron or minus 2 electron, it's dropped down to 20%, and the rest is really negligible, right? So this is the concept, and it changed due to the diameter of the particle, okay? And so actually in my experiment, I compare the charged aerosol with the non-charged aerosol, and I know that my aerosol actually charged with around 100 electron, and using this neutralizer, this is a device that have a corona that make a lot of ions and bring my aerosol to the neutralized state. And I know that after using the device, I changed the electricity effect by 2 orders of magnitude. So now I can compare. It's like on-off effect in my experiment, okay? קבוצת בקרה, control group, okay? So I already told you that this is a time phenomena to neutralize charges or to charge charges. So we have some exponential decay in the charge, and we have this time constant, which again related to the mobility and the concentration of the ions. You can, of the ions, and if you're gonna have NIT approximately equal to 6 multiplied by 10 to the 20, this mechanism gonna take a second around. You know the time estimation, tau gonna be 1 second, which means 30% of the procedure already finished. So 2 seconds, 3 seconds, 5 seconds, it's 90%. Okay, and in the atmosphere situation, this can take around 1.5 hours to actually get a neutralized state when particles get charged into the atmosphere. Okay, so I'm gonna take to you a little bit about the position of electrostatic effects with the example of the lungs, but it could be anything. So most of the time when you go to the doctor and you have a problem, he's gonna give you some inhaler to treat you, right? And inhaler, as we talked before, is actually gonna an inhaler actually gonna enhance the electricity effects of the aerosol. It's gonna charge it. When you use inhalers, you actually use some windows of some narrow windows of sizes that the inhaler can actually hold. And as we talked before, we have all the force taken into account, but you have also the electrostatic effect force. And why so? Because when the aerosol get from the small nozzle with a really high velocity, they get charged by that, by triboelectricity, which means the friction effect. Okay? And from many devices, according to the literature, we can understand what is actually the amount of charge per particle. For nebulizer, it's around 10 electrons per particle. For DPI, it's 200. MDI, it's 500. And you can have some academic ideas that gonna enhance the charge effect, which can reach to a huge amount. And the question is how we can use this concept to actually enhance drugs to the lungs more efficiently. Okay, and so there's two main electrostatic deposition mechanisms. One of them is actually related to repulsion, and the second one actually to attraction. Okay, so the first one, the attraction one, is when you have aerosol next to some conductor. In my case, it's the tissue of the lungs, the epithelium, right? So you're gonna actually have effect of image charge in the conductor. I'm gonna show it to you in some example. For example, this is what I do for my student for physics 2. This is a aluminum, which is a conductor, right? I hope it's gonna work. And right now, using friction, I'm gonna charge this PVC. And right now, the electron actually distributed in some way. I hope it's gonna work. And if they gonna be close to each other, you're gonna see some attraction between them. You see that the can is moving without them touching it. Try to roll it, right? So what's actually happened is the electrons on the aluminum actually try to get closer to the charged particle, and this actually make a force. Okay, so we have some. We can actually use a model that use image charge, which means there's a really weird motion of charge on this conductor, but I don't care. I can actually flip the problem to another problem, which say that I have the same charge with opposite sign on the other side, and then calculate it's going to give me the same solution. Okay? It's using the idea that the potentials should be the same, and you play with it. And so if we're going to use Coulomb law, we can put the distance to be twice the distance from the wall, and from here we can get the force of this induced effect. And if we're gonna, I don't think that we have time for that, so we're gonna skip it, but if you want, I have the slides here. And if we're gonna do some, I'm gonna take the force equation, and I'm gonna do non-dimensional analysis with drag and gravity. I'm gonna get this number, which is non-dimensional number that tell us how much dominant this effect in our problem due to scales, length, time, and everything else. Okay, and if we're gonna compare this to stock, for example, or compare it to gravity, we're gonna see for a small particle this effect is really dominant the game. Okay, and I did here some simulation on the lungs. So here you actually see how depth I am inside the lungs, which means this is the trachea, this is the split between lung left and right, this is the lobes, and this go on and on and on and on until you get really deep into the lungs. And you see that the electrostatic effect doesn't play any role. You can see that we have some point that gravity actually take over stock, right? But if you go deep inside the lungs, okay, you're gonna see a point that electrostatic actually dominant gravity. And this is the more dominant effect, and the reason is that if you remember electrostatic effects, we have on the denominator R squared, right? The distance. When you go inside the lungs, everything gets small and dense, small and dense, small and dense, until the distance between particles, between the tissue, is really, really small. And that's the reason this mechanism, the force, gets really, really strong, okay? And of course you can engineer this using the charge, using the size, using the velocity. And the other mechanism is called the space charge effect. The space charge effect said that particles, if you're gonna have the same sign, gonna repel each other. Okay? So if you're gonna zoom into this tube, yeah, it could be just any any tube, not a lungs, but the particle would like to repel each other and go to the edges, right, and deposit there. And how we can estimate the value of this force. So we're actually going to look at the concentration of the particles in order to understand what is the distance between them. So opposite to concentration, we can get the distance, the mean distance between them, put it in the equation, and do the same force analysis, and get this number, which actually tell us what is this effect play. And I want you to see that it's really depend on the concentration of the particles. And what's happening in the lungs is that this effect die really quickly, because the amount of concentration of particles inside the lungs actually get diluted as you go inside, more and more volume. So for that reason, this is like the concentration when you go inside the lungs, right? So what's happened is most of this effect take part in the upper part of the respiratory system, which means the mouth and the throat. And so you can see here that they did here a cool simulation when they play with the charge and want to see the effect of the deposition. And this is actually the mouth, right? The mouth and throat. And they see that when they increase the charge, you have a lot of deposit particles in the mouth and throat. And this is taking into account also the space, also the ink idea. And you can see here that the overall the position that you have when you add the electrostatic effect is increasingly huge, especially for a small particle, for the reasons I told you before. Gravity effect gets small, impaction getting small, and electrostatic get dominant. You can see here another example of half of a micron. You can see here multiplication of 3 times the depositions. In my experiment, I have this setup, okay? I have, as I told you before, a aerosol generator, dryers. Then I have the neutralizer, which can control the amount of charge that I want in my experiment. And then I have this model which mimics the flow inside the alveoli. That's the idea. Alveoli, it's the end of the lungs. Okay, it's the smallest place that we have in the lungs, and this is where actually oxygen get into the blood and CO2 get outside of the blood in this location. So the idea is I mimic the same velocities that we have in the alveoli, and in this part I actually build a small alveoli system. Okay, same half of spheres, and this is some simulation to understand what is the velocity that we have there. So this is the profile. We have separated flow inside the alveoli, which means we have a flow that goes that way, and we have some spiral field of velocities that go inside the cavities. And also what I did, I put some covering on the glasses that make it conductive to actually see this effect and be more to be in the same situation that we have in the lungs when we have the tissue as a conductor, right? So I put ITO, and I also put grounding to the model, okay, not to accumulate charge on the model itself. And you can see here, for example, this is just a flat model that what I have a huge amount of particles when I use electrostatic effect, and a really small amount of particle when I don't use a charge. And you see
where
that
are the particles? You have
what I did here, it's just a flat model, okay? Just
so these are deposited particles?
Deposited particle, yes, deposition fraction, and I just number the particle on each part, and you see that here you have a fashion of a big drop, like particles deposit more and more and more, and here you have the effect that it's kind of linear, it's kind of I would say a dish knob to the surface. And what else? And this is what I did when I put the alveoli. Okay, when I did the alveoli, which means the cavities, I see a huge difference in the deposition percentage in the alveoli compared to charge and not charge. So this I think is the more interesting part. So when I compare the ratio between what's get inside the alveoli compared to the space between the alveoli, I see that with charge it's multiplied by 4, this ratio, and the pattern. Was that? And I also track the location where the particle deposits. So I want to remind you this feature. So what I saw that with charge, I have this kind of a population of particles inside the alveoli, but without it, I have this kind of phenomena. So you see it's difference in a numbers particle. This is around 20, this is 100 and something. And you also see kind of a drift to this size compared to evenly deposit on the alveoli.
What is X here?
X is the location, the projected location of the cavity of the lungs.
So
Like
X
this.
is where it will be deposited.
Yeah, yes. So you see here a lot of evenly deposition, and you see here like kind of a drift, but you also see that the amount is really negligible. It's 1 order of magnitude less than this effect. Okay, and that's it. That's pretty much.
How do the particle get into the alveoli? They have to pass through the...
They need to cross the streamlines and get inside. They can do that by gravity or by a Brownian motion, or thanks to electrostatic effects that pull them inside. Yeah, that's the concept.
So why doesn't it attach to some other place? Like,
What?
so why doesn't the particle attach to, let's say, upper respiratory tract or something?
Again? Why
So
the
you have
particle?
The particles
Yes.
are charged, right? The
Yeah.
end goal is to make it deposit at the lower end, at the smallest.
In this, I said that they can deposit everywhere in the lungs. Yes.
Yeah.
This enhance deposition in general, but when this electrostatic effect is gonna be more dominant than everything else, is when the distance gonna be small. This especially happen inside the end of the lungs, which is the alveoli region. Yes, that's what I said. So
But
what's
the
your
question
question?
is, why did the particle reach till there? Like,
Most of the time when you breathe aerosols, it really depends on the velocity, the speed, and other factors. But a lot of the time when you inhale small aerosols, the one that's gonna be affected by electrostatic effect, you actually inhale something and then it get out. It doesn't touch the walls. It doesn't deposit most of the time. Yeah. So most of the particles. So by using this mechanism of electrostatic, you actually enhance the chances for particles to actually hit the wall and deposit. Because the particle, if you're gonna see the relaxation time, they're gonna go with the flow. They're gonna follow the streamlines. Okay?
one more question: how do you measure the charge on a particle? Like, do you track the deflection or something?
This is one of my problems. I really want to measure the charge of my particles. When it go outside of the neutralizer, it's really easy because I know the distribution of the neutralized charge at the steady state. It's really easy. But my charged particles, I don't have a really good way to measure it. The only thing that I do, I have other papers that use similar system to mine that actually had the devices to measure it and tell me around what is the average, and that's what I assume. But I would be happy to actually think about a way to measure the charge more precisely. It's going to be super cool.
What do you mean?
What?
You can measure the charge
How?
Deflection,
by...
right?
It's really hard to build this device.
yeah,
Yeah.
it's true.
It's really what's happened. I have a pen. Yes. Can you turn the camera to this side? If you want to do, it's not working. And this, okay. So what you said that take a particle, right?
Yeah.
And put some electric field and see where this particle is actually ends up. And
Yes.
from this distance, you can understand what was the amount of charge.
Yeah.
Let's do a capital D, right? So the problem with that is that the particle is sensitive to a lot of stuff. Like if you're gonna do this kind of system, you have this kind of streamlines, right? So the particle would follow this thing. So what you actually need is to have this kind of device. And this could be another PhD to build these kind of devices because it's sensitive to many stuff. To build a reliable and to buy one is really expensive.
But you can measure charge. The charge will be simpler to measure than the distance. I mean, if you know that particle can carry charge, and charge can be related to, of course, to current, you can...
Yes, exactly. You want to put ampermeter
Yeah.
here and to measure the concentration of particle that I have using CPC, for example. and from that to get some estimation, saying I had I is dq to dt, right?
Something like this. Yeah.
Stuff like this, and from that, doing integral over time on the current, I can actually understand how much charge I had divided by the concentration and have some estimation what is the charge. This is a good way that I want to talk about with you. So I would like to have your opinion about it. What ampermeter, where I can buy it, which kinds.
The problem is not this. The problem is that everything is statistical because you actually cannot measure one particle.
You're gonna say it's kind of average, yes. Yeah. And also you can get 0. It doesn't mean that you don't have, you can have 50.
Most of the particles have 0 charge.
Yes, actually maybe in my experiment I have 100 and minus 100, which is a lot of charge. But together when I'm gonna measure the current, I'm gonna get 0. So this is not gonna tell me the true
But when you
nature of the.
when you say that the particles are charged with 1 electron, this means that the Boltzmann distribution is such that particles between particle with 1 minus or plus charge and 0, of course, are probably, I don't know, 95% of the distribution or 80% of the distribution. That's what you mean.
Yeah. So that's it.
That was very nice.
Thank you.
Thank you.